Okay, so let's start with today video. So today we will look at the classification and logistic regression, right? So let's first understand what kind of data set will fall into the classification problem, or what is the classification problem. So in classification problem, uh, the output will be discrete. So or you can say output will be in form of labels, right? How But in if you have already looked into the regression problem, then if you have observed in the regression problem that output is continuous in regression problem, right? If I give you an example, uh, of estimating the house price given the land area, so here the output is house price, right? And the house price is continuous, right? So but in a classification problem, that output y is not continuous, it is discrete. And what could be the example of the classification problem? So one example we can take, like, given a email is spam or not. So maybe you are getting the emails and you have to classify those email that is spam or not. So given an email, that email is spam or not, right? So maybe few emails will be the spam and not spam, and few emails will be in spam folder spam. So it is based on the uh, in the content, what content you have in the, like, lot of thing that we can capture from the email content, and we can verify that given email is spam or not. So that is the different thing. But here if you look at the output has the two label, 0 and 1. So here y belongs to either 0 or 1, right? So this is the classification problem. Let me take one more example. Suppose given a tumor size, you will have to find that based on the tumor size that uh, cancer is malignant or not. So that is also a classification problem, right? So I hope you have got the idea about what is classification problem and what is regression problem. And it is not necessary here that y will take only these two value. It may take maybe three labels, like -1, 0 and 1. It may take 4. So it depends based on your data set, how many classes you have in your data set. So that such that you can divide your data sets into label, right? So this is all about the classifications. Now what we will do, we will focus on this binary, right, where output will have the two labels, yes or no, positive, negative, 0, 1. So we will focus on this, and we can call it like binary problem, right? So if you see what I have written here, that just like regression problem, except that y we now want to predict take on only a smaller number of discrete value. So in regression problem, r belongs to the the y belongs to r, so it takes complete value. But in classification problem, that y will take some discrete value. So now we will focus on this binary problem, right? So, and in binary problem, given the data set, so this is the data set, how we can indicate this data set. For I is equals to 1 to n, the output will belong to 0 or 1, either 0 or 1, either positive class or negative class. and this we also called it the labels for trainee examples, right? This yi, so it has two labels, 0 and 1. Okay, now the binary problem, what will be the example? That example I have already explained you, that the spam classification of email, right? Okay, now now the question arises that can we use the same approach that we have used in regression problem? uh, what we wanted to do in linear regression is to minimize the error, right? So we wanted to our hypothesis function uh, closer to our data points, such that overall error should be minimum, right? According to that, by adjusting the parameter, we fit the line and we get the best fit, such that overall error is minimum. So this is how we approach in linear regression. So now question is, can we adopt the same approach in classification problem, where we can classify the labels of output using the regression, uh, using same way that we have already done in linear regression? So we can do that, but that is not an efficient approach. So what will be the problem? Let me explain you. So let's take an example of this. Given the tumor size, data is given that given the tumor size, the cancer is malignant or not. So if you see that there is two labels here, so no and yes, right? So now what we will do, we will try to fit uh, we will adopt the same approach what we have done in linear regression. What we will do, we will make our hypothesis function such that, or by adjusting the parameter, we will make our hypothesis function such that uh, the overall error is minimized. So this is as theta x, right? If you recall that, then you will get to know that how. So by updating the theta's value, that theta 0, theta 1, we fit this line such that the overall error is minimum. So so this is the best fit for this given data set. Now what we have made, that we will take this as a threshold point, and what we will say that if suppose a new data came, suppose a patient came and it has the tumor size that belongs to here. Now what we can do, we can map this here and we get the value that is less than 0.5. so we can say that the that given the tumor size, that patient have what that malignant cancer or not, right? So it has the threshold here, right? So based on that, we can make the decision, right? Given the tumor size, it is malignant or not. So now this is the approach that we have already looked into the linear regression problem. Now question is that, can we use the same approach for our classification problem? So what will be the problem? Let me explain you. Problem will be, what will be the problem? So suppose you have the outliner in your data set. So this is the outliner, right? Now you will run the linear regression, right? You will run the update the theta value, theta 0, theta 1, and you will get the hypothesis function, right, as theta x, such that the overall error get minimized. So this is your new hypothesis function according to the given data set, right? Now you see the problem. let me tell you what's the problem. So earlier, uh, so okay, okay, sorry, this green line is the old hypothesis function, right? This one is the old that for this given data set. Now this outliner has came into picture. Now what will happen that this line, uh, so now the best fit is this yellow line, right? This yellow line. So now the best fit is this yellow line. So you see that earlier it was the threshold point was somewhere here, now the threshold point is here, right? So there is shift in your threshold point also. So the we can say that we do not have the fixed threshold point where we can make the decision, from where we can make the decision. So overall point is that that outliner is affecting the threshold point, right? So uh, so overall we can say that we cannot use the linear, we can use, but depending on the data. So the main point is that it is not appropriate to use the linear regression approach in classification problem, right? So that outliner will affect your, in your hypothesis function, and that the threshold point will get shift. Okay, now if you observe that our output, if we take the binary problem, then whatever the input is, whatever the input is, output will be in the range 0 to 1 or 0 and 1. It will take the two value only, 0 and 1. So now okay, now what we want to do, we want to we want our hypothesis function such that so whatever input you give to your hypothesis function, it should lie in between 0 and 1. So we want h theta x belong to 0 1, since y belongs to 0 1. Now we don't want h theta x to take large value, right? Greater than 1 or smaller than 0. So that hypothesis function is now bounded between 0 and 1. So how we can get this? So we can use this function, right? That is h theta x is equal to g theta h theta x is equal to g theta transpose x, and this is the function, right? So and also, so let me first explain you what is this, what this function will do. So now we can change the hypothesis function. Now we have this hypothesis function, and how we define this g, this function gz is 1 upon 1 plus e to the power z, and this function is called the logistic function or sigmoid function. So now simply in place of z put put this theta transpose x, right? So overall point is that earlier our hypothesis function was h theta x is equal to theta transpose x. Okay, so this was the hypothesis function. Now what we want to do, we want this hypothesis function to give the value in between 0 and 1. So what we will do, so if you look at this gz, so gz will have maximum value. If we put here what will be the maximum value for this gz, it will be, if we take z as infinite, then it will be 0, right? So if we take the infinite value, then it will be gz will be 1, and if we take the minus infinite value here z, then it will be 0, right? So uh, gz will belong from 0 to 1, right? So now what we will do, in place of z we will put this h theta x, right? And this is nothing but theta transpose x. So this is what we have done. So now our hypothesis function h theta x is equal to 1 divided by 1 plus e to the power minus theta transpose x, right? So now if we plot this gz, so uh, it will take 0 value uh, when it extends towards minus infinity, and it will take one value when it extends towards plus infinity, right? And at 0 it will have 1 divided by 1 plus 1, that is 0.5. So now uh, so this function, that hypothesis function, will is always bounded between 0 and 1. Now let's look at one useful property regarding this sigmoid function. If you take the derivative of this sigmoid function, this is what you will get the derivative. So gz 1 minus gz. So it will be useful in case when we will do the derivation, right? So now question is, given the logistic regression model, how do we fit theta for it? So what we want to do, we want to fit we want to calculate this theta 0 and theta 1. Okay, once we have this optimal value of theta 0 theta 1, then we can fit this curve to our data set, right? Okay, now if you look at this h theta x, so h theta belongs from in case of logistic regression, it belongs from 0 to 1, right? So we can map the hypothesis function to probability. So what we can say is what we can assume is uh, that probability y is equal to 1 given x. So since y can take value 1 and 0 depending on the value of x, so uh, so we are putting those two cases in form of probability. So y can take 1 given x, that is h theta x. Then what will be the probability that y can take 0 given x? So obviously it will be from the basic as axioms of probability, we can write 1 minus h theta x, right? So also we can write these two in one equation. So probability y given x parameterized by theta is equal to h theta x y and 1 minus h theta x 1 minus y. How we you can think, so y can take only two value, right? So y can take 0 or 1, right? So when y is 0 given x, then this will be 0 and this will be 0, then you will left with this term only. So this is what you will get, right? Now when y is 1, right? So when y is 1, then y probability that y equals to 1, so if you put here 1, then this will be 1 and you will get this, right? So we can write this as, so these two are the same thing. Okay. Okay, now let's assume m trainee example were generated independently. So so let's assume that so the overall point is that we want to find this theta 0 and theta 1, right, to fit this curve into this data set, right? So how we can approach this? So now we will talk about this. So let's take that whatever uh, those points in those data in your training set example that are generated from some distribution, and those are generated independently. Okay, now then likelihood function will be joint probability of those data sets. So how we can define the likelihood function is it will be the joint probability of those given m trainee data set, and these trainees data sets are getting generated from some distribution, and each trainee example is independent of other trainee example. Okay, now how we can define this likelihood function is the joint probability of all those generated points in your training example. So if they are independent, then obviously that how we can write the probability of a intersection b intersection c. If they are independent, then we can simply product them, right? A probability of a into probability of b into probability of c. So same way we have written here, right? So probability of y given x. So suppose first trainee data set is x1 and y1, then probability of y given x1, then into probability of second trainee data set, then third, right? So again we can, using this we can write like this, right? The same thing as theta xi yi into 1 minus h theta xi 1 minus yi, right? Now okay, so what we want to do is to maximize the likelihood function, right? So we want to maximize the likelihood function. And why we want to maximize the likelihood function? So if you have gone through my previous videos, then you will get to know why we are maximizing the likelihood function, right? So again we will not maximize the likelihood. What we will do, we will maximize the log likelihood, and we are taking this log likelihood as small l theta, right? So simply what we will do, we will take the log of this, right? So we will take the log of this. So simply I have taken the log of the whole thing. Now if you break down this log, then you see that these are in the form of multiplication. So overall that if you take the log of this, right, let me just take the log of this. So how you will take the log e to the power h theta x I y I, right? So this yi will come in front and this will remain same. So this is how I have written, right? Same way this will come in front and log of this will be there, right? Okay, now we have this small l theta. Okay, now for maximizing, now what we our aim to maximize this l theta, that is log of likelihood, right? So we can now this is the optimization problem, and now what we will have to do, we will have to maximize this l theta. What we can do is we can use the gradient ascent. So if you have looked in linear regression problem where we want to minimize the cost function, Now here what we, and what approach we have earlier used to minimize the cost function is the gradient descent. Now here we want to maximize the likelihood function, and what we will use is the gradient ascent. So instead of taking minus sign there, we will take the plus sign, and this is the update. So how we update in the parameters. So let's suppose that theta 0, this will be the theta 0 new, and this is the theta 0 old, and this is again the learning rate, and this is the gradient of L theta, that is the log of likelihood. So okay, now let's calculate this, the derivative term, right, this one. So how you will calculate? Okay, so what we will do that okay, let me see if I have done it uh, classification, right? So okay, so I have already done. So okay, so we want to calculate this derivative, right? Del of del theta I L theta, right? So simply we will take the derivative of this, right? So let's look at, you can do it simply, it is simple. You can use the chain rule and you can easily do that. So first of all, so we will have to differentiate with respect to theta, right? So this is the log term, and in the log term it is theta transpose is there. So what is the differentiation of log x? So it is 1 upon x, right? So here you will get the 1 upon g transpose x, and y will be as a constant. So now using the chain rule, what you will do, you will take the differentiation of this inner part, this inner. So this is how I have written differentiation of del theta upon g theta transpose. Okay, now we are done with this, the first part, and now let's come here. What you will do, simply you will take the first differentiation of this thing, right? So it will be again 1 upon x. So the whole x term is 1 minus g theta transpose x. So this is 1. Now you will go inside and you will take the derivative, right? So this is the derivative of this. Now if you see that these two terms are common, right? So you can take it as a common here, and whatever the term you will left is this, right? Okay, now if you recall that the derivative of the sigmoid function, this is nothing but the derivative of the sigmoid function. And if you recall that we have already kept this derivative of sigmoid function, that is gz into 1 minus gz. So you can make use of that, and you can write the derivative of this sigmoid function, that is gz and 1 minus g theta transpose x. Now you see that again you will go inside, right, and you will take the derivative of this theta transpose x. So derivative of this, so derivative of this del upon del theta j theta transpose x, right? So you will get the jth term, other term will be 0, right? So okay, yes. Now what you can do is okay, so what I have done is simply multiplied. So what will happen, that these term will cancel out. So this one and So these term will cancel out. This one when you will do the multiply, so here it will only y and this term is again in the multiplication, so it will be here, right? Now you will multiply this with complete this one, then this term will get cancelled, this one and this one, right? And you will left with 1 minus y and this, right? So this will cancel out and you will left with this one, okay, and xj will be there. Now you can simply do the multiplication and y times y and 1 minus y times this, so these terms will get cancelled and overall you will get this. Now this g theta transpose x is nothing but this is your hypothesis function, right? And that is equal to 1 minus 1 plus e to the power minus theta transpose x. So we can write this as h theta x into xi. So if you observe that the update rule is same as what we have done in the linear regression in cost function, right? So the update rule is same, theta j is equal to, or theta new is equals to theta old plus alpha times, that is learning times, that is your actual output, and that is your estimated output. So overall this term is error, uh, and this x of j, right? So here now if you see that but what's the difference? So this update rule is same as the least mean square, right? So what's the change here? So change is in the h theta xi. So this is what the hypothesis function will look like, and this hypothesis function is non-linear, right? And in case of least mean square, where we use to minimize the cost function, that h theta x is the linear function, right? So this is the difference. So even though this update rule is looking like same, but we have the difference here in the hypothesis function, right? So okay, so this way, using the gradient ascent, you will get the parameter theta 0, theta 1, theta 2, whatever the parameter you have, that you will get from this update, and that will maximize your likelihood function, right? So that way you can okay, so once you will get this theta 0 and theta 1, then you can fit the threshold point, right? So okay, I think that is all in the classification problem, classification and logistic regression. So that is the logistic regression. Okay, we will look into next lecture. Thank you.